Morning, Year 12. We are going to learn today about what an electrolytic cell is. So let's get started. For this, you are going to need your redox booklet, and we're looking at page 24. I'm just going to cut to whiteboard. Okay guys, so we are looking at electrolytic cells. So I'm going to start, we're just going to look at our zinc copper electrochemical cell that we've looked at before, and we know that in this one, zinc has a higher electrical potential than copper. So it's a better reductant. I don't know what I'm doing here. Okay, it's a better reductant. And so our electrons are going to flow from the anode to the copper cathode, and we will generate a current in the wire because this is a spontaneous reaction. But what if we wanted to use this cell instead of using this cell to generate an electric current? What if we wanted to make zinc from this? How could we use this setup? How can we use it so that we were actually, instead of the zinc corroding, we were getting more zinc? What if we wanted to get a zinc plating on that? What we have already happening is we've got zinc going to zinc ions, and we've got this being the spontaneous reaction. What if we want to send it back the other way? If we want to send it that way, then that would be the non-spontaneous way. Remember last video we talked about how we need to apply energy in that case. So the reason that the zinc's corroding is that the zinc is negative. Zinc has a negative charge here, and the copper has a positive charge, and of course electron flow goes from negative to positive. How can we make the electron flow go the other way? Well, it's simple. If we want the electron flow to go the other way, then here we are with our electrode, our zinc electrode here, and our solution here has Zn2 plus in it. How we make the electrons go here is we have to make this negative and this positive. But that's not the spontaneous way it is. So what we do here is we actually put our power pack in here. That's a power pack for those that didn't recognize it. And we've got our little red and black terminals. Oh, I have to be red and blue today, I haven't got a black. So if we want to, we need to actually connect this to the positive terminal. Come on, work. So we need to connect that to the positive terminal of the power pack. And we need to connect that electrode to the negative terminal of the power pack. And if we do that, the power pack is going to supply the energy to change the signs on those electrodes. And then our electron flow is going to go from negative to positive. Now, when we put a power pack or we put an electric supply in there, this now becomes what we call an electrolytic cell. Okay, so this is now an electrolytic cell. Undo that. Okay, so we're going to use electrical energy to force non-spontaneous reactions to happen. And the process is called electrolysis. Oh, auto shape. Electrolysis. So what we're going to learn about is electrolysis. If we go to your booklet, notice that we have an external source of energy. That's our power pack. And we're looking at non-spontaneous reactions. So electrons going the non-spontaneous way, or backwards, if you like. Now, oxidation still occurs at the anode, and we just changed the anode sign, and the anode sign is now positive. So the anode sign is positive because we're connecting that to the positive terminal of the power pack, and the reduction is still going to occur at the cathode. Let's change that to at in the book, shall we? But the sign of that's going to be negative now. Anions are going to move towards the anode, and cations are going to move toward the cathode. We don't have half cells, so no half cells. You always have both electrodes immersed in the same electrolyte. So we can draw this as both electrodes in the same electrolyte. Do you know your battery notation? The bigger one is the positive, and the little one is the negative. So this is now the anode, this is now the cathode. So they've just changed sides, but the anode is still going to have oxidation, and the cathode's still going to have reduction. That red cat and ox always. So don't forget, red cat and ox. That never ever changes. So let's have a look at comparing galvanic cells and electrolytic cells. So remember, this is the natural way the electrons flow. This is the forced way. So in the galvanic cell, we've just talked about how our anode, in the galvanic cell, our anode's negative and our cathode's positive. In the electrolytic cell, that changes around, because remember, we are actually controlling the direction of electron flow by connecting to the power pack. So this is positive terminal of the power pack here, negative, so positive here, negative here. But notice, oxidation occurs at the anode and reduction at the cathode in both of them. No difference there. Okay, electrons are going to flow from the negative terminal to the positive terminal, and that's going to be the same. So both of those, it's just that we controlled, using our power pack, we controlled which was the negative terminal. We didn't just let natural electrical potential decide that. We decided it. So we're forcing it to happen. So reactions are spontaneous. So the E0 EMF, or the electromotive force, also called the voltage, we've called it E0 cell. That's positive, and therefore we get a natural flow of electrons from the anode to the cathode. Here the reactions are non-spontaneous. Non-spontaneous, so if you did the E0 cell, it would be negative. And remember, a negative E0 cell says doesn't happen naturally. Okay, what do you use them for? Well, we've already looked at the use in batteries. I'm sure you're sick to death of looking at batteries right now. When we use an electrolytic cell, we use it for electroplating, and that's always a fun prac. And also purifying metals or obtaining very reactive metals. The only way you can get sodium is by electrolysis. Okay, there is no way to actually separate sodium from its compounds unless you use electrolysis. And that's what we're going to be focusing on in our next video. So I'm going to end this one now, and we'll continue with looking at electrolysis of molten salts next time.